Remember the formula is QVB sine theta. A little note on theta. Yeah, in most questions, theta is 90 degrees, and that's implied somewhere in the question. If it's less than 90, that's going to be very clear because it'll be given a number, that 30 degrees or 60 degrees or something like that, right? So if we look at a graph of sine theta, right? Here's the sine curve. At 90 degrees, it's a maximum. So that means that the maximum magnetic force will occur when theta is 90 degrees. So sometimes a question will be worded like that, like what's the maximum magnetic force the particle could experience or something like that. And then by the virtue of the word maximum, you need to know that sine theta is 90, or theta is 90, sorry. However, if you have 180 degrees or 0 degrees, that means that the force is 0, because at 180 or 0 degrees, then sine of theta is 0. And that means that, you know, if the angle is 0, that means you're parallel. They're running in the same direction, so there's no angle between them. So you're looking at parallel. So magnetic force is a maximum when the field and the motion are at right angles to each other, and then you have circular motion. Or there can be no magnetic force if the charged particle is running parallel to the field. Okay, so if that's the case, then you have a force of 0. So if it says, if you see the word parallel or 0, either one of those things means that the force is 0. All right, let's look at this one. This one's going to be fun. So an electron accelerates from rest through a parallel plate. So imagine this is the situation, then it's allowed to escape. Okay, so it accelerates through the plate apparatus. It leaves here and it enters a field that is into the page, that's what I mean by the X, of 0.2 teslas. By the way, teslas are usually about that range, or often of that range, typical number. Okay, so first we want to know V2. We're looking for this speed right here, as soon as it enters the magnetic field. Okay, these questions, you see them frequently. If you don't see, you'll see it on either, or, and, all of the above, test, exam, problem set. You can assume there's no magnetic field in here, and you can assume no electric field right here if you see a question like this, okay? Anyway, so we want to know V2. That's the first thing. Then it asks us to find Fm. Okay, we can do that. That's just the formula, QVB sine theta. And find the radius. Here we go. Find the radius of the electron's circular path. That gives us a hint that our sine theta is going to be 90 degrees. It's implied in the question already. We know the thing's going to move in a circle, and we want to calculate r. But we'll get to that. Let's first find that speed, okay? So, strategy. Use the electric field information to find the speed. Use that speed to find Fm. And then from there, you say Fm has got to be equal to Fc, centripetal force, and solve for r. Okay? So part A, since we know potential difference in one speed, we can use conservation of energy to find V2. So there's our formula. We learned it a couple days ago. Solve for V2. Okay? You can pause, but I'm going to move on. Typical number, I'm going to check mark that, by the way, because 4 million meters per second for a, what is this? Electron. It's not that unusual. Okay, magnetic force. Now wait a second. How do I know it's sine of 90? I know the Q, I know the V, I know the B. How come I know it's sine of 90? Let's see. So it's moving horizontally, okay? And the magnetic field is into the page. So if you think about that, those have got to be at 90 degrees to each other, right? And again, no angle given is the quick answer. Okay, so there you go. There's our tiny, tiny force. And the direction, so it's electron, so I use my left hand. Flat palm, fingers into the page, following the magnetic field. Thumb points to the right. And so my palm now is facing down, so the force is downward. And there's my answer. Tiny, tiny number, which, again, it's electron. It should be a tiny, tiny number. So I found A, my speed. I found B, my force. Now I'm going to find the radius of the circular path. So again, that means that Fm equals Fc. I'm looking for R. So R is going to be mv squared over Fm, just if you look at this formula. Just get R by itself. Plug in all the numbers, and it's tiny, tiny, and it is typically in the range of milliliters. So that's normal, and that's how you do it. Good answer. Okay, one more example. No, two more examples. Same thing. Calculate the speed of a proton moving in a circular path of radius 8 in a plane perpendicular, so there's my 90 degrees, to a 1.5 Tesla magnetic field. Same question, but in reverse. And so I think you should pause the tape and try it on your own and check your solution. Here's the solution, but I'm going to go through the solution. I think you should pause first, though. So here's all my information. 0.08 meters, obviously take my centimeters into meters. It's a proton, so that's the charge. There's my Tesla, perpendicular, 90 degrees. For part A, I'm just looking for V. But now it's kind of going backwards. What voltage would be required to accelerate to that speed? So I'm looking for V, and then I have to say, then I have to use the conservation of energy to find my voltage. So, you know, I find speed equating magnetic and centripetal force. I mean, we're talking about a radius. It's given a circular path. That's got to be the case. There's no other solution to be had. So solve for V. Very fast, but still within the range of a number I'm used to, so I'm going to use it. Find potential difference using this formula. Anytime you're given speeds and you're looking for or given a potential difference, this has got to be the formula. 630, it's a big number, but I actually do know that to be, we've seen numbers like that before with the voltage, so it's all good. Okay, so check your answer, make sure it's all good, and moving on. This is an easy question. I just wanted to use it because it's a different type of application. We're talking about real stuff here. Earth has a magnetic field. It's itty bitty. It's not very strong, 5 times 10 to the negative 5, but it's there. And we want to find, we know the speed, we know the charge on the plane. Could require a charge just due to friction, right? Static friction. Calculate the maximum magnitude of magnetic force. So maximum means sine theta. So we're traveling perpendicular to the force, sine 90 degrees, and the maximum force is a Newton. And it's hard to say, you know, just by looking at the number if it's a good one. But you know, if you look at the note here, you know, 100 times 200 times 10 to the negative 5 makes sense. It's around that order. Excuse me. So that's the last example on magnetic force. You can go try some on your own now.